Okay, so nomenclature is really just a fancy way of saying what's the name of something. So this really leads to sort of the cumulative nature of chemistry. So we're going to write the name or write the formula, and then we're going to do balancing, which is making sure the number of atoms match. And then we're going to switch, right? So then we're going to do quantities, where we are going to actually look at how much is used in a reaction, how much is produced. So, and it's all going to be based on the chemical formula. So that's why in a normal semester, I choose to do naming quizzes, because it's really important that you can see what the name is. So on the back of your periodic table, there is the chart of polyatomic ions. And so some of them, hopefully maybe you remember, things like hydroxide are often found in bases, so maybe you remember that one. There are some weird ones that we actually do use a lot in grade 12 and grade 11, which is chromate. So sometimes people, that messes them up because it's a sort of a weird ion, but chromate, dichromate, and then there are some that we use all the time. Hydroxide, nitrate, phosphate, ammonium is the only one that's positive. All the rest of them have a negative charge. So you always get to have this chart. And then, like I said, we are going to manipulate some of the polyatomic ions, which you may have done in grade 10. Okay? So we'll start with the simple ones. And so I did talk about this when we first talked about electronegativity, but the element with the electronegativity is written first. So that's why we say things like sodium chloride, not chlorine sodiumide. Okay, we put the metal first because it has a lower electronegativity. And the chemical formula tells us the number of atoms, which is of course important for what we're going to do next, balancing. Okay, so there are many elements that have a very straightforward ionic charge. So we used to have this when I started teaching. We had this old textbook for grade 9, and that's really where you first start talking about ions and stuff like that. And it actually called the charge bonding capacity, which is a very outdated way of thinking of how elements come together, because there are unfortunately quite a few exceptions, but that's okay. So a quick way to figure out how elements will bond together is by their ionic charge. And as you continue on, sometimes people will call that valence number or their oxidation number. So in grade 12, we're going to talk about redox, or oxidation and reduction as a way of looking at reactions, because of course transition metals, we often skip counting their columns. They have that strange electronic structure. So for elements like calcium and oxygen, you can predict what their charge is going to be based on the column. So you do need to remember that metals will be cations, right? So they're always positive. So whether it's a transition metal or not, anything to the left of the staircase is going to be positive. And then non-metals are negative, or they're anions, right? So that's important. So again, if you mess yourself up with counting the columns, then right now, if you haven't already, write it on your periodic table. The column with hydrogen is going to be +1. Every single element in that column is going to have a charge of +1. The second column will be +2. It's going to lose 2 electrons. So calcium has a charge of +2. It's an alkali earth metal, and it doesn't matter. I don't care what you do. You can write it like that. You can write it like this. For our purposes, when we do the crisscross rule, that's incidental. It doesn't matter. So transition metals are a problem, okay? So this periodic table, if you choose to use ours, you have to look underneath. So underneath copper, which is 29, There's copper 2 and copper 1, okay? You can see the 2 and the 1. Sometimes they only have one charge, like zinc only has a 2. Silver, which is Ag, only has 1. Manganese has 5. So they have a very unique, remember, delocalized, no pattern to their electronic structure, okay? So how do we deal with that? Hopefully, for sure, your grade 10 teacher at least did Roman numerals. We'll talk about a few Latin names as well here. And what you'll see now is if you look at the transition metals, some of their charges are underlined. So copper has its 2 is underlined, nickel its 2 is underlined. And what that is that's the most common charge on copper ions. So it doesn't really matter for what we're going to do today, but when we do single displacement, when a metal is by itself, single, then it can be tricky. How do we know what charge to use? So then the default we go back to is using the common charge, okay? So that's why some of them are underlined. But something like this, it's telling you, this is the number 2, so it's copper 2. Okay? So your periodic table will be your best friend, especially if there's a transition metal, you might need to use the table, okay? And then oxygen, so again, if you want, at the top of your columns, remember we had to, when we talked about reactivity, it was sort of the outside and then you move in. Ignoring the noble gases, they don't react naturally, so we're not going to include those. So fluorine's column has a charge of -1. Oxygen's column has a charge of -2. Nitrogen's column has a charge of -3. Yes. Oh, sorry. You mean that? Thank you. So, and then carbon's column, what do we do with that? We will deal with that when we get to covalent, okay? Carbon will share electrons. So we're going to use the prefixes mono, di, tri, etc. And then when you do those, you don't crisscross, right? So we'll talk about that eventually. You may notice that some of the nonmetals have more than one charge as well. So what we're going to talk about in grade 12 is how when you have sharing electrons, we already talked about nonpolar and polar, equal and unequal. Well, sometimes sharing can be so uneven that the electrons actually come from, like the pair of electrons comes from one of the atoms. Sharing can always be a little wishy-washy. So even though nitrogen, sulfur, etc. has more than one charge underneath, for what we're going to do here, you just count the column, okay? Don't worry about those weird charges. Okay, so when you have an ionic compound, whether it is a transition metal, alkali earth metal, it does not matter. So you write the metal first because it has the lower electronegativity, and then the nonmetal goes second. Again, most people are used to sodium chloride, so you don't say chlorine sodiumide, right? So think about an example that you already know. So when you have an ionic compound, you are going to crisscross. So we are crisscrossing the charges. And when you add them together, you should get an overall charge on the compound of 0. So we did look at that when we talked about ions, that there's a mathematical way to figure out what how things should go together. We actually already also did Lewis structures. So let's say you had calcium and chlorine. Okay, so calcium, you would have said, had to lose 2. Chlorine only gains 1, so you need two chlorines. Right? So this relates to doing this. crisscross. Okay, so they go together. So another thing that's insanely important for ionic compounds is that you reduce the subscripts. And I was speaking to a grade 10 teacher, and she said she didn't really stress that or focus on that, but it's very, very important, because now you know that that the structure is going to change. Okay, so what do I mean by this? So the easiest or most famous, I guess, example is magnesium oxide. So magnesium is 2. It's an alkali metal, earth metal, like calcium. Oxygen is -2. So when you crisscross, technically you get Mg2O2. Okay? You cannot leave it like that, because if you had the Lewis structure, magnesium loses 2, oxygen wants to gain 2. Are there 2 magnesiums and 2 oxygens? No. So this, you cannot leave it like this. You have to reduce. Okay? So even if your grade 10 teacher said this was fine, it's not fine. Okay? Because that's not really what happens. So please make sure for ionic you reduce the subscripts. So if you're a highlighter, or you have, make a box, make it stand out. And that's really, those are the 2 differences. Crisscrossing and reducing subscripts. We are not going to do that for covalent, okay? So at the top of the worksheet, it talks about, there's like, do you crisscross charges, and you circle yes or no. These are just trying to get you to see to remember for yourself the differences between ionic and covalent, okay? Okay. So sometimes people get really fancy and they'll say binary ionic compounds. What does binary mean? 2. Okay? So technically, when we get down to polyatomic, they are going to behave like ionic as well. We're going to do the crisscross rule and stuff like that. But poly means many, right? They're going to have many different, more than 2 types of atoms. So this is just being very, very specific. So we only have 2. Okay? So when you have ionic compounds, you do need to check if it's a transition metal, but these ones are not. So we'll just do these simple ones first, and then the transition metals are the next slide, okay? So here we have lithium and oxygen. It's already been crisscrossed. So really you just have to remember, and I to be honest, I won't take marks off for this. If you wrote lithium oxygen, I wouldn't take marks off, but technically you should write IDE, but I won't take marks off for that. Sodium bromide. So again, you kind of have to decide how much work you need to show, if you can see it in your brain. So the final answer for this is just NaBr, okay? But if you need to write out the crisscross rule, write it out, okay? So sodium is Na, it's in the first column. Bromine is a halogen, which means it's -1. So, you can decide for yourself as well. Do you want to write the 1 or don't? So let's say in math, if it was x to the power of 1, we don't write the 1. Same thing here, but I won't take marks off. If you write Na1, Br1, that's fine, okay? But you don't have to. So now when you crisscross, these are both the same. We cross to the bottom, right? You don't write it at the top, but you can just write the final answer of NaBr. So, and maybe right now you're like, ooh, I need to practice this, but by the end of the day, you're like, you know what? I can see it now. Sodium is a really common metal. You'll probably be like, I know what its charge is. Not that you ever need to memorize the periodic table, but you just might find that some of them you're used to. Again, it's one of those things where when you get to grade 11, sometimes students are like, oh my goodness, I remember this, I got this, I can see it, okay? You got big grade 11 brains. So this one is just calcium oxide. This one we just did, but I'll do it again, okay? So you do need to remember to reduce subscripts. Even if you forget, really, if you forget which one's positive and which one's negative, even if you just wrote the number, that'll work too, right? Because we don't cross the positive and negative, so who cares? Okay, you cannot leave it like that. You have to reduce. For the normal or representative or common metals, like the first three, like the first two columns, and then say boron and aluminum, maybe gallium you'd see, then there's not really, this is probably it. Okay, it'd be like a 2 and a 2 and you have to reduce it. Once we do ones like tin, which is SN, and lead, which has 4s, so, and unfortunately they're also pretty common elements, then you might actually have to do, like you could have a 2 and a 4, and you would have to reduce one of them, you know what I mean? But when you have normal metals or ones that you can count the columns for, this will be as big as the reduction will be, okay? So there's not a lot of variety, right? There's a column with +1, a column with +2, and a column with +3. The variety comes when you have a transition metal. Okay, so this one is aluminum. And sulfur is one of those things where sometimes it's spelled with an F and sometimes it's spelled with a PH, and it doesn't matter. Okay, so you can write either of those. I feel like your textbook uses this one. I would call this more Canadian or more metric system, like UK and us, but it doesn't matter. Okay, so not too bad, not a lot of variety. The problem is with transition metals. So what happens when you have more than one charge? I've included here tin and lead. So in your book, I think it called them other metals. If you happen to watch Brain Pop, I think they call them semi-metals. They're at the bottom here. Okay? And they are common elements. Tin we use all the time, right? Lead, unfortunately, we use all the time, even though it's really can cause developmental delays, but we do use it. It will block radiation, so it does have its purposes. So these two at the bottom, they definitely have, we're going to treat them like transition metals, but they're a little bit off to the side, okay? So you just need to make sure to keep those in your head. And so when you have a transition metal, if you use our periodic table, it's found underneath. I believe the one at the back of your textbook, it writes it at the side, like this, I think. That's a common way to do it as well. But we have to tell you somehow what the charge is, okay? So they are going to lose electrons, so they're all positive. So we're going to do two things. So the stock method is using Roman numerals. And then we are going to learn 5 Latin names. And you might say to yourself, isn't the stock method, well, stock implies sort of that it's the same everywhere, first of all. But what happened is, back in the day when they first were looking at elements, things like lead and tin were easy to find and easy to use. Things like copper, gold, okay? So they gave them special Latin names because Latin was considered to be the language of knowledge and intelligence, right? So unfortunately, even if you're like, oh, I could Google it. Yes, sure, you could. But if you Google copper 2 sulfate, for example, you'll often find it as cupric sulfate. So as a scientist, it's important to know both, okay? So we'll do Roman numerals first. So again, this is hopefully at least the bare bones of this your grade 10 teacher talked about. I guess the only weird thing is if you're not familiar maybe with Roman numerals, so it's like 1, 2, 3, 4 is like that, 5, 6. I think 7 is the highest. Yep. If you're a Super Bowl fan, maybe you're used to Roman numerals. Even iPhones, the iPhone X is really the iPhone 10, right? That's 10. But for us, there's only the highest charge is manganese with 7, and manganese is not very common. So usually it's 1, 2, 3, or 4, okay? Those are the most ones that you're going to see. So when you have a name, so if it's giving you what the name is, then it'll be in brackets. And if it's not, if you're given the formula, then you kind of have to uncross. So it is a little bit more, it takes a little bit more brain power, okay? Okay, so for the Latin name, there are 2 endings. Iconos. So again, if you like cheesy ways to remember things, gigantic, I don't know. So these iconos can only be used for elements that have transition metals, that have 2 charges only. So something like manganese doesn't work because there's 5. Zinc only has 1, doesn't work, okay? So it has to be those that have only 2 charges. So like I said, usually these are saved for ones that have Latin names, again, because they were so common. So if you look at copper, copper's symbol is Cu, and that's because when they first discovered copper, they called it CuP, so coupe, not copper. And then silver is called, its Latin name is argentum. Okay, so those symbols are related to their Latin names, okay? Technically, I think the one I use on there is nickel. Technically, you could do this for any of them, like you could do Nikolic and Nicholas, but why would you do that, okay? However, you can, if you have to write the name for a compound with a transition metal and you're like, oh, I like Latin names, go ahead, okay? It doesn't matter. So whichever charge is smaller, you use OUS, and whatever charge is higher, you use IC. Whether you do stock or Latin or Roman numerals or the Latin name, you're still going to follow all the rules. You still do crisscross, you still reduce the subscripts, so all the rules. Okay, these are ionic compounds because it's a metal and a non-metal. Okay, so you do need to memorize these 5. But like I said, it's sort of, the clue is really in the symbol, okay? So copper symbol is Cu. Its Latin name is Cup. So there's the Cu, okay? So then copper has 2 charges. Whether you're fancy and write it like just like this, or if you write it with the, like that, it doesn't matter. Same thing, okay? So this one is the lower charge, so cuprous. Oh, sorry, those are cup and cupric. Usually copper's pretty straightforward. I would say tin is the one that students often forget for whatever reason. Maybe because the symbol looks nothing like tin, I don't know. So tin has 2 possible charges, tin 2 and tin 4. So those are the charges underneath its symbol. So the symbol for tin comes from its Latin name, stan. Okay, so stannous and stannic. So lead's Latin name comes from, it's plumbum, because, so literally like plumber, like they used lead, even the Romans used lead in their pipes because it was easy to manipulate. It's a pretty soft metal. However, it makes people crazy. So the Mad Hatter is, the character from Alice in Wonderland is mad because they used to put lead in hats. So like literally right beside your brain. Okay, so not good. But anyways, so this comes from plum. So lead also, like tin, has 2 and 4. So plumbus and plumbic. Usually lead students remember. And again, this one's a little bit easier because, I mean, it's kind of in the symbol. I don't know what it is about tin, but that's definitely the worst one. Okay? And then we have iron and gold. So iron is Fe because iron is black. So the Latin name, or the Latin word for black, is fair. So iron has 2 and 3. So ferrous and ferric. Iron 3 oxide is rust, ferric oxide. So again, maybe, in your travels you've heard that word before. Rust is something that plagues us as humans and when we use metals, so definitely studied extensively, especially us in cold climates with salt. So the minute you put salt on the roads, then if you have like a nick in your paint, then your car can rust or corrode even faster. Salt accelerates that, so does water. And then gold, the Latin name is ore, again the AU, so usually students are good with this one. Gold is 1 and 3, I think. Yep. So again, all 5 of these metals were something that that early scientists, even early alchemists studied, okay? Can we make lead into gold? We use lead for pipes and hats and stuff like that. Copper is very malleable and ductile as well, conducts easily, so conducting heat, like they would have made pots out of it. Iron, they made, blacksmithing. That was, the whole thing was manipulating iron. And again, you could do this for anything, any transition metal that has 2 charges. And so I think in the textbook or maybe the worksheet, one of them is Nicholas and the other one's Nikolic, okay? But why would you do that? Just use Roman numerals. But it doesn't matter if you like Latin, it's up to you. Okay, so we'll do 2 examples. So again, when you have a transition metal, then you kind of have to uncross. So these 2 look virtually identical. The 2 down here came from the iron, same thing with this 3. So that tells you the charge. Sorry, I just squished there. So if you were given this, and I didn't say write the Latin name, which I never would, you can choose which you want, okay? I don't care. I think in the worksheet it says try to write both, just so you get the practice, but you don't need to write both, okay? But you do kind of have to think uncross. This 2 came from the iron, and you can always check. Go and look. Iron, oh, what's its charge? It's 2 and 3, right? So then you can kind of check your answer. You never need to memorize the periodic table, okay? So then this would be ferrous fluoride. And ferric. Again, it sort of looks weird here. So even if you were like, what do I do? Go to copper. Copper has 2 or 1, and then you're like, oh yeah, there's no 1 written here, but that's what's understood, right? Okay, so we'll just do covalent or molecular, and then I'll give you a chance to do some work, and then we'll do the other ones after a few minutes. So if you prefer to call them molecular, it's the same thing, it doesn't matter. So these are going to be nonmetals. And again, sort of not a beef, but that seems harsh, but I'm going to call it a beef, with the grade 10 teachers. Sometimes when they first do these, they'll actually try to do it with crisscross rule. And yes, maybe you can do that sometimes, but you can't do that all the time. So when you do covalent or molecular compounds, there is no crisscrossing, no reducing the subscripts. We're going to use prefixes. So as long as you remember what the prefixes are, these are actually very straightforward because you don't have to uncross. You don't have to reduce. You just look at what it is and write the appropriate prefix, okay? So some of them will be ones, again, that you've heard before. So 1 is mono, 2 is di, 3 is tri. You would probably know that, right? 4 is tetra, 5 penta, like a pentagon, 6 hex, like a hexagon. Sometimes people will put sept because of French. I usually don't mark that wrong, okay, but it is hept. Oct, like an octagon, and then 9 and 10, they are rare, and so sometimes these are the hardest to remember, okay? Nona and deca. And then if you, chemistry grammar, so to speak, like say it's oxygen, we usually just say like decoxide, not decaoxide. You don't have to put two vowels together, but again, something like that, I won't take marks off, okay? So no crossing, no reducing, just look at what it is. Nitrogen and oxygen, this cannot be crisscrossed. This does not make any sense. We're going to talk about how this forms in grade 12, okay? Nitrogen monoxide is a big deal. It is a greenhouse gas making acid rain in our atmosphere, okay? So this is a thing. So the convention is, for whatever reason, when the first element is only a 1, we don't usually write mono, but you can, okay? Because the second one, you have to. So you can't just write nitrogen oxide. You have to write nitrogen monoxide. Again, we don't write monooxide, that's weird, but if you do, it's okay. If you want, if this screws you up and you want to write mono, then do it, okay? Most people, again, try to think of ones you know, like carbon dioxide. We don't write monocarbon dioxide, right? But if you want to, go ahead. So now this one, who cares? Does it crisscross? Who cares? We don't care, okay? So sharing, strange, weird things can happen. So this is meant, hopefully, you're like, okay, this is easy. How many P's are there? How many phosphoruses? 2, which is di. Again, phosphorus is one of those ones where you might see it PF. No, P. Oh, and no S, OUS. And again, OUS, US, doesn't matter, okay? And then 5 is pent. And again, if you write pentaoxide, that's fine. It's just a little bit weird chemistry grammar, okay? Carbon dioxide, CO2. So now this one, the penta goes with the sulfur. Tri goes with the chlorine. Don't cross. Don't worry about that this doesn't work. Covalent compound sharing can often not work, okay? So pentasulfur is S5. Chlorine, 3. Okay? All right, so if you go to the back, you'll find naming worksheet number 1. So you can work on that. The solutions are already on D2L, but I'll get them up on that green bulletin board as well if you hate D2L or if the Wi-Fi is not working or whatever. If you love the textbook and you would prefer to do textbook questions, they're all the same. If you want to do as much practice as humanly possible, then do as much as you can, okay? And I'll do your breaks at 10:35. I don't want to wait that long, so maybe we'll start polyatomic at 10:15, okay?